Fitting. Um, he is working in New York, I guess, and he is famous for being pioneering the Tableau method. He has written books about this, and in 2012 he won an important award, the Erbron Award. And I have not enough time to list all the merits of him, but now we hear an interesting talk by him on the family of strict tolerant logics. Please go ahead.
Okay, thank you very much. It's a pleasure to be here. Um, one thing a bit different about this talk, many of the, possibly all of the preceding talks involve research that's gone on for many years. I don't know to what extent people in this audience know of strict tolerant logic, but basically the whole subject is something on the order of 5 years. So this is quite recent work. So it began with a logic called ST, which is strict tolerant. And I'm going to begin by explaining what others have done, and then what I've add what I've added to it. So strict tolerant, all right. So it's this will be propositional and just conjunction, disjunction, and negation and the connectives. Sequence will have their usual syntax, bunch of formulas, arrow, a bunch of formulas. There are no structural rules. This is not proof theoretic. It's all going to be semantic. And it will be helpful to, if you think of a sequent really as a representation of a kind of Scott consequence relation. So classically, the sequent gamma arrow delta is true with respect to evaluation. Think classical logic here, assigning truth values to propositional letters, provided if V makes all of gamma true, then V makes something in delta true. That's the standard definition. Now, true is true. Both sides of the sequent are held to the same standards. And using the words strict and tolerant suggests that's going to change. What strict tolerant logic does is hold antecedents to stricter standards than consequence, where things are more tolerant. Think something like the way a physicist operates. You think of the laws of physics that you're following as strictly true, and the consequences that you draw from them that you want to experimentally verify as true in a looser sense, as you need a margin of error there and then you'll say, yes, I got this. So let me do the details. And when I say everything is semantic, it's because I'm going to move to generalizations where often proof methods don't exist. So semantic is all I've got to work with. So let me begin a little more precisely with classical logic, which is a part you should all know. And then I'll broaden it from there. So for the start, you have these two truth values. And think of them as ordered from left to right. There's a greatest lower bound operation, a least upper bound operation, and there's an order reversing operation, which typically gives you your interpretation for and, or, and not. There's a designated truth value, and that's it circled. And okay, so this just is what I said. The lattice operations interpret conjunction and disjunction, and the order reversal negation. And evaluates to true means evaluates to that designated value that I had circled. And I'll say evaluation V satisfies gamma arrow delta. Classically, that's what the C is to suggest, provided if V maps every member of gamma to that designated value, then V maps some number of delta to that designated value. And I'll just say the sequent is valid if it's valid for every valuation, validated by every valuation. Now, strict tolerant logic. And this is not my work, this is well, call it classical, the 5-year-old work that led up to this. if you just have two truth values, you don't have enough flexibility to it. So strict tolerant logic is a three-valued logic. And the three-valued setting, this is the lattice associated with it, ordered from left to right. There's a middle value. It's an intermediate value. You have the lattice ordering from left to right. Conjunction is still going to be interpreted by meet, disjunction by join, and you have a negation, which is an order reversal. But there's actually more than one logic based on this structure. The Kleene strong three-valued logic has these as its operations, but the designated set of truth values is just T. And that's going to be the strict designated set. That's why the subscript S is on the D there. There's also Graham Priest's logic of paradox, which uses exactly the same connective definitions, but takes this as the designated set. So you can think of it as it's designated if it's not false. So here the T suggests tolerant. Kleene's middle value was essentially undefined, and Priest's middle value is overdefined, or contradictory. But if you stand back enough, they have the same truth tables. It's what they differ in their designated values. Now, strict tolerant, and I'll say evaluation V validates this sequent gamma arrow delta in the strict tolerance sense. That's what the ST is for. If if it maps all the members of gamma to the strictly designated set, it maps some member of delta to the tolerantly designated set. So the strict in this case is just true, the tolerant is not false. And the sequent is simply valid if it's validated by every valuation. Okay, so that's strict tolerant logic as it's been around for a couple of years now. And the central results that others proved is strict tolerant logic and classical logic in fact validate the same sequence. But they differ at the metaconsequent level. Specifically, they differ on cut. Now, there you have to be a little careful. This is cut, as you've all come to know and love. But there's a local version and a global version. The local version is each valuation mapping the two premise sequence above the line to true maps the sequent below the line to true. And the global valuation is if every valuation maps the two things above the line to true, then every valuation maps the thing below the line to true. We tend to confuse them in classical logic because they both hold there. But in strict tolerant logic, you have global cut, but you don't have local cut. There's also a tolerant strict logic, which is more recent. And it shouldn't be terribly surprising that it switches around the roles of strict and tolerant. So here the premises are held to more tolerant standards and the consequence to strict ones. And the connection between tolerant strict logic, and I won't bother writing the definitions out, they're exactly what you think they would be. Tolerant strict logic and classical logic anti-validate the same sequence. That is, a sequent is anti-validated by a valuation, is anti-validated if no valuation makes it true. So tolerant strict logic and classical logic have the same anti-validities. And again, results of others, there's a hierarchy here. We have sequence. You can have sequence of sequence. For example, cut as a rule could be represented as a higher level sequent where you've introduced, in this case, arrow star. There's a strict tolerant at level 2 for these meta sequence. So the gamma 1 star, delta 1 star are themselves sequence here. And this is a validation V validates this in strict tolerant level 2, provided if V validates each thing on the left in TS, then it validates something on the right in ST. Notice the asymmetry there. This is something like a strict tolerant one level up. And again, ST agrees with classical logic on metasequence, but differs from it on meta-metasequence. There's also a tolerant strict level 2, there's level 3, and so on. So there's a whole hierarchy of these, which agree with the behavior of classical logic at higher and higher meta levels. So you can think of the strict tolerant sequence here as approaching classical logic from the validity side, and a similar tolerant strict sequence as approaching anti-validity. But they don't actually coincide at omega. You can go on into the transfinite, but that's work of others. Okay, I'd forgotten. I actually say this here. Don't bother reading it. And the question, what is strict tolerant good for? Well, here are a couple of examples or questions. Vagueness. The standard Sorites paradox. Okay, let me use the paradox of the heap. You have a heap of sand. How does a heap behave? Well, if you take one grain of sand out, it's still a heap. But if you keep doing that often enough, it's not a heap. And this is a standard problem. And strict tolerant logic has been proposed for use here because you have the sequent level, it behaves exactly like classical logic. But since you don't have local cut, you don't have the kind of transitivity that leads to this iterating, removing, causes problems. The formulas don't combine. More interesting, and this has caused a lot of arguing, what exactly do you mean by a logic, or when are two logics the same? The Tarski answer is they're the same if they have the same consequence relation. But here you have two that agree on consequence, but I wouldn't want to say they're the same because they don't agree at the meta level. Well, okay, so you could enhance Tarski by saying, well, you should throw being the same at the meta level too. But then you have this one, which agrees at ground level and next level, but not the next level. So there's a question, just what does it mean for two logics to be the same? This is not my argument, but it's being argued in the literature a lot. Okay. Now, what I want to do is get to my contribution. So I'm going to go past all of this background work. And what I've contributed to this is the recognition that this is really a very general phenomenon. Strict tolerant logic in much of the literature is that one logic, the three-valued logic that I showed you. But in fact, there's a broad range of logics that have exactly the same phenomena. So let me just give some quick refresher on many valued logics. The standard, nothing unusual here. You have a space of truth values. Some of them are designated. You have some way of interpreting propositional connectives, and you have a notion of valuation that respects the interpretation of your propositional connectives. Now, I don't want it in this generality. I want it to be lattice-based. So I'm going to be using the Morgan algebras, and that three-valued and two-valued logic structures from earlier are really the simplest examples here. De Morgan algebra, you have a bounded distributive lattice with a De Morgan complement. I say this, but then I realized I don't actually use it. But anyway, so you have bounds, you have a meet, you have a join, and there's complementation, the De Morgan complementation. It's order reversing, and it's an involution. So actually, I don't need distributivity. And Arnon, you should be familiar with this. It's because you have a representation theorem for bilattices that doesn't use distributivity. So I'm going to use the term Morgan algebra. If somebody knows a more standard term, please tell me. But it's a De Morgan algebra that, except you don't require distributivity. I'm calling it Morgan because dropping the D is to suggest dropping the D from distributivity. Morgan algebras are what I'm going to use as my space of truth values. So the meet is always going to be interpreting conjunction. The join is always going to be interpreting disjunction. The Morgan involution is always going to be interpreting negation. If we have a Morgan algebra, a subset is upward closed. If, well, there's the definition, it's upward closed. And I'll say the pair LD, where L is a Morgan algebra and D is upward closed, is an upclosed logical De Morgan algebra. So L gives you your truth values and D gives you your designated truth values. And I'll say evaluation in that thing validates the sequent gamma arrow delta in a standard classical sense. If it maps every member of the antecedent to a designated value, implies it maps some member of the consequent to a designated value. Okay, all of this is absolutely standard many-valued logic stuff. Now, strict tolerance structures, instead of a designated set, there are two designated sets, which you should expect. L should be a Morgan algebra, so that's your space of truth values. T should be a proper non-empty subset of that, and S should be a proper non-empty subset of that. And you can easily predict how you're going to define validity in a structure like that. Evaluation V validates the sequent in the strict tolerance sense in such a structure. If it maps every member of gamma to S, then it maps some member of delta to T. And I'll symbolize this as in this strict tolerance structure, in the strict tolerance sense, V validates gamma arrow delta. And I'll simply say the sequent is valid if every valuation validates it. Now, here's the central result. When I said this is a more general thing than just ST alone, start off with an upclosed logical Morgan algebra. There is a strict tolerance structure that validates the same things as the Morgan algebra validates, but differs from it at the metaconsequence level. So I'm using this notation C of LD and ST of this other thing. So every upclosed Morgan algebra has a corresponding strict tolerance structure that validates the same formulas, but differs from it at the metaconsequencery level. And then you should look at the notation here. The strict tolerance structure, L star, D, D star, these have relationships to the Morgan algebra you started with. Oh, yeah, important fact. There's actually an algorithm for constructing that strict tolerance structure, starting with the Morgan algebra. Now, I said there's a relationship between these. The set of truth values in the strict tolerance structure extends the set from the original Morgan algebra. If you restrict the operations from the strict tolerant case back, you get the original ones. If you think about the ST in classical logic, if you restrict the operations of ST, the Kleene three-valued or the Priest three-valued, if you restrict the operations there to the classical value, they're just the classical operations. This generalizes that. The domain here, the L star, the truth values, and the tolerant truth values themselves form an upclosed logical Morgan algebra. The strict values are simply the original designated values. And the tolerant values restricted to your original values are your original designated values. So the connection between these is quite tight. And again, think about it in terms of the original ST. The hierarchy results that I mentioned earlier all extend to this general setting. No change in wording whatsoever. Now, I said there was an algorithm here, so I want to show you some examples. If you start with classical logic, what the algorithm gives you is ST. So you've already seen that. ST is usually thought of as constructed starting with Kleene's logic and Priest's logic. Well, those themselves are logical Morgan lattices, so they themselves have strict tolerant counterparts of their own. So strong Kleene. Okay, so these are the three truth values. I'm writing the order vertically now instead of horizontally. And this is its designated truth value. These are the truth values of the strict tolerant analog of it. What have we got here? 6 truth values. This is supposed to extend the original lattice, and you see there I've marked F, M, and T out. They're the original, correspond to the original. The strict set of designated values here is supposed to be the original designated set, so fine. And this is the tolerant designated set. So the strong Kleene validates the same things that this validates in a strict tolerance sense. And again, they'll differ at the cut level. Priest's logic has the same underlying lattice, but this is the designated set. For this one, the corresponding lattice, it's the same as it was before, because the strict tolerant lattice that you get only depends on the lattice you started with and not on the designated values. But this time, okay, the strict designated values and the tolerant. And again, these two validate the same sequence, the one on the left in many valued sense, the one on the right in a strict tolerance sense. And again, these differ at the cut level. First degree entailment itself, 4-valued logic, again, ordered upward, with these as what are usually taken to be the designated values. This is the lattice for the strict tolerant counterpart, and the corners are what correspond to the original one. The strict ones are what the designated ones were originally, and this now is the tolerant set. So again, these validate the same things, the one in a many valued sense, the other in a strict tolerance sense. This can be taken further. For ST, somebody realized somewhere along the line that instead of using Kleene's strong 3-valued logic together with Priest's logic, you could use weak Kleene and a weak version of Priest's logic. Well, that also extends, provided you're starting off with a logical Morgan algebra that's orthocomplemented. That is, X or not X is 1 and X and not X is 0. Now, this, of course, is an incomplete statement. ST can be modified to use Kleene's weak 3-valued logic. What is the analog of Kleene's weak 3-valued logic that I'm using here? And many years ago, I introduced a family of generalizations of Kleene weak 3-valued logic arising from bilattices. And that's the one that works here. Also, the strict tolerant results, the original ones, were extended to quantificational and modal logics. And all of that extends to this general setting, that is, a modal logic where truth values of a world are calculated using one of those logical Morgan algebras, for example. Now, how does this get proved? Okay, I'm not going to show you, but I'll just sketch what is needed, because the proofs generally are the original proofs that people gave. What is different is finding the right structure in which to carry the proofs out. So here's what's involved. I'm using bilattices. They don't, the bilattices aren't mentioned in the results, but they're the essential tool for the proof. The bilattice product of a Morgan algebra, with itself, okay, the algebra, bilattice product algebra gives you a bilattice. Such a bilattice has what I called some years ago a consistent subset and an anti-consistent subset. You need the information ordering on a bilattice for this. The consistent subset is the set of things that are below their conflation, that's the symmetry in the knowledge direction. The consistent subset and the anti-consistent subset are isomorphic, so either can be used here. That's what you want as the truth values for the corresponding strict tolerant logic. The original upclosed set on the Morgan algebra generates in a natural way a bi-upclosed set on the bilattice. And what you want to do is restrict that to either the consistent or anti-consistent part, whichever you've chosen to use. And that's basically the setting to use here, in which case the original proofs carry over, mostly with changes of terminology, which is surprising. So my contribution here really is to find the right home for this. So there actually are an infinite family of examples. And the question is, to what extent can this be moved beyond simply a many-valued setting? Is there a kind of strict tolerant analog for, say, intuitionistic logic or relevance logic or something like that? But at any rate, this is already pushing it fairly far. And it says this problem of saying what identifies a logic is really a rather broad question. It applies to this whole family, not just to classical logic. But anyway, what are the positive uses of all of this? Well, vagueness was an example, but in the generality that I'm discussing it, I really don't know. So, but I think it's interesting, but I don't know if it's any good for anything. And so let me conclude by giving some references here. And when I said this is recent work, I mean, if you look at the dates on these, the logics of strict tolerant logic, 2015, the hierarchy results that I mentioned were published in 2020. Chris Gambler introduced investigated this dual notion, the TS logics and anti-validity in 2020. Dave Ripley's is the oldest one here, this observation about the failure of cut and the application of ST to the Soriates paradox. That's 2013. I have 4 papers here. The first one, Arnon, this is in a volume for you, and it hasn't come out yet. So there are later papers. The one this talk is mostly based on came out last year. The one on weak Kleene just came out, and the one on quantifiers and modalities hasn't come out yet. So that's it. Thank you.
Yeah, thank you very much for this very interesting talk. Now we have lots of time.
Oh, you're frozen.
What?
Hmm?
Yeah, so who wants to pose a question?
Oh, okay, here.
Ah, yeah, okay. So, I see, Sergey, you want to pose a question?
Yes, but not necessarily want to go first. Either anyone, because it's okay.
Well,
I'll break the
I
ice.
could ask a question and then you could go.
Oh, okay. Well, imagine then. So imagining. I remembered once Tolis Lysenko, he was here when he was asked to give it to pronounce Russian toast somewhere in a very tense situation. He said, "I'm pronouncing an empty toast." It was a very wise decision. So we still remember it with Lena. Lena is just laughing on the back. Yeah. The question is about hyperintentionality. Does this approach capture, or is it capable of capturing hyperintentionality?
I haven't the foggiest idea. I never thought of it in this context.
Because, well, here's the feeling. The feeling is that you mentioned intuitionistic logic. And
no work in this context has been done yet.
I understand, but as a possible direction. And my experience in dealing with intrinsic logic semantics, at least with its original BHK style semantics or proof semantic, is that it has a very strong syntactic component. It's not about truth values, and this manifests itself not only in the ancient Gödel's observation that it's not finite logic of the tabular, it's not matrix, there is no finite amount of truth values, but also in all further things. The Kripke semantics is fine. Oops, it's, yeah, I was pressing the space bar for too long. The Kripke semantics is not hyperintentional. So it's basically, you can substitute with equivalence. The Fitting semantics, which is the workhorse, the standard, the gold standard semantics for justification for logic of proofs, and eventually for intrinsic logic with BHK, from the BHK perspective, is hyperintentional. And my feeling is that what this direction steers toward to the usual intentionality rather than hyperintentionality. And if so, then maybe something like the fitting model component, which is a nice, the obvious witness component, would shed some light on the thing and may be useful also for intrinsic logic or for a large variety of other things.
Okay, I haven't thought about this at all, but I did say there was a modal version of all of this, and I said I'd be interested in starting there and seeing where that led.
Yes, because there is some feeling in logical circles from the philosophical side that hyperintentionality is the way to go.
Yeah, yeah.
And it's quite strong feeling. So that's in this respect. Me neither, I didn't think about it too. And each time I hear you talk, Mel, probably more often than any people present in this room, but each time I learn something new out of it. And not only because you're a fantastic speaker, but also because I'm probably too lazy to open my windows to new ideas as all old guys. So we have to be a little bit more open. And so your fine explanation about strict intolerance and comparing strong Kleene logic with the priest logic, it's really just kicked me immediately. It went to the right place. Thank you.
I have a question too.
Yeah, please go ahead.
First of all, I want to say that I'm sure that can be a lot of applications, but I'm also more interested in the philosophical part. So about this difference between the levels, meta level, etc. So do you have, or other people have, a definition, given a logic, what is the meta level of this logic? Well, how do we decide that, for example, classical logic cut is valid also at the meta level, for example? Is it true also if you add quantifiers, and because on the level of first order, there are two kinds of consequence relation associated with classical logic. So it might be different level, different meta level in each case.
Yes, of course. I've myself had problems fully grasping what this hierarchy is doing. To what extent do you actually get to specify what is happening at the hyper level? But if you allow yourself to do it, you know, specify, okay, these are the conditions up to a certain level, after which we default to the way we usually do things. You get interesting logics, but perhaps different in form than we've looked at before.
Yes.
And I'm still struggling to try and understand what's natural there.
By the way, Mel, the book is going to be published very soon now. And one more comment to you at the end, what you're talking about application, remind me one of Girard's best claims. In one of his papers about linear logic, he said explicitly, we have the answer, we are looking for the question.
Uh-huh. Quote.
Yeah, maybe one more remark, Andres. It's just a quick follow-up. When you mentioned that you don't have time to list Mel's achievements, you don't have time even to list all his books.
Yeah, I can imagine.
How many of them are now, Mel? Do you keep the count?
No, I think it's somewhere around 12.
Yeah, 12. Well, certainly good. Sorry.
Well, anyway, there's another question. Professor Yun, who are you? Please ask the question. You are muted. Please unmute yourself. Yeah, now you may ask a question.
He's not muted, but the microphone doesn't seem to work.
Well,
Okay, give me some time to fix it. I will get back. I will get
Okay,
back.
No,
just
it's
speak
not
up.
working.
Speak up. We can hear you, but just speak up louder.
How about this?
Yes, that's fine.
Okay, thank you.
Keep talking and I will tell you.
Too high technology.
Please ask the question.
Have universal quantifier on valuation at the outer side.
I'm sorry, I can't make it out what you're saying.
Say it again, but really just yell. Just loud, very loud.
So you just meant two kinds of cut, one called local cut with universal quantifier to the outer layer and the implication in the inner layer, and also the global cut, which is an implication but with universal quantifier both on the antecedent and succedent part. So I just got an idea that if we can sort of group the valuations, then we can have two layers of.
I got you part way through, but I can't fully make
I will repeat. So far, what he said, that you considered local cut and global cut, and Junhua has an idea. If you introduce group semantics, okay, then what?
Since we still have some time for the next talk, may I just type my questions out instead?
Absolutely, just type in for everyone in the chat.
Okay. Sorry for the inconvenience.
Yeah. Sure.
And maybe in the meantime, if somebody else has a question, we can.
But also this indicates the problem, because Junhua Yu himself is a speaker tomorrow, the first talk, and so the mic should be fixed, because we can tolerate the question typed in the chat, but I don't think that typing the whole talk in the chat.
Yes, I will
Oh,
take care of it.
yes,
I will
yes.
take care of it.
Please check this out, Junhua.
Sure, sure, sure. I will
Well,
check
by
my-
the way, I
Local
can hear you
computer.
better. Shall you try?
What?
Try to speak, because it seems that at least I can hear you now. Okay, go ahead.
I think I will. I think I will change my device for tomorrow's talk. So now the voice is good.
Yes, the voice is good somehow.
Oh, so guess it's the problem of internet connection rather than hardwire. Okay, so my question is like this. You just mentioned two kinds of cut. One is local and one is global. So it's just in different places of universal quantifier and with the implication. My idea is that if we can sort of group the valuations, then we can have two layers of universal quantifier. One for group that goes like the local to the outer side, and one goes for members inside of the group, and that we can put in the global style. So will that add some sort of new dimension, or is that meaningful? It's just the idea that I come up minutes ago.
Well, it's reasonable, but it's kind of like the local and global distinction in modal logic. And your use of quantifiers really corresponds to the use of all worlds and this world. It's a notion that turns up in a lot of contexts.
Thank you for the answer. Thank you. And by the way, I think I will change another device for tomorrow's talk. It's really inconvenient. Sorry for that.
And then test it, Junhua, please.
Yeah, test it before the session with
If you
people,
tested good, yes.
with the local people. Just make a mock presentation and just to see how it works.
Maybe find an environment with a better internet connection or more reliable internet connection or
I
something.
probably will move to my office instead of my dormitory.
Okay,
Thank you.
I know that you know your problems better than us.
Yeah. Thank you.
Anyway, are there further questions? Well, if not, then let's thank Melvin again. And there's a question at the end. That's fine. So we have still some minutes. So Professor Speransky.
No, it was just.
It was just thumbs up, right? I mean.
Okay. That's hands up. Okay, that's perfect. So then I would suggest to have a welcome break. So we restart at 7 o'clock sharp with Professor Bartz. And now we have 15 minutes break, which is fine because we